Are there any benefits in cancelling good factors? We will answer that in this video. Welcome. We will illustrate that with an example. What are the possible benefits of cancellation? We know that good parts of the plant will become a part of the controller. In the video where we defined good and bad factors, we obtained the following control law. So at least some part of the controller is good, namely AG and BG. If there is no cancellation, there is no such guarantee, such good parts will not appear. Is there any benefit because of this? That is a question we will address in this video. For this, we will consider this particular case study, and we require the plant to have the following closed loop characteristic equation. It should have non-zero offset to step inputs. The plant already has an integrator, so no additional integral mode is required. We will begin with our cancellation approach. We will now design the controller with cancellation. This is the plant. We will split this into good and bad parts. This is BG 1 minus 0.8 Z inverse. BB has a negative 0, so it is taken as bad. 1 minus 0.5 Z inverse is taken as good. This factor has a 0 on the unit circle, so it is taken as bad, and K is 1. We have to solve the Aryabhata's identity. So we need to substitute for AB, BB, K, Phi and so on in the next equation. So AB is given here 1 minus Z inverse, Z power minus 1, K is 1. For BB we write 1 plus 0.9 Z inverse, and then this is Phi. Solve for R1 S1. When I solve this, I get these values, and the 0 of R1 happens to be in a good location, which is inside the unit circle with a positive value. Finally, we obtain the following 2-DOF controller. I would want you to go through the calculation and verify all the steps. So I implement that controller using this file dof_choice.sce. Next, we will consider a controller without cancellation. Recall from the example video in the PID week, we had the plant as B by A and GC as SC by RC. The denominator of the closed loop transfer function is 1 plus G GC, and when I substitute for G and GC, I get this, and simplify it, I get this. Next, we equate the numerator of this to Phi CL, the closed loop characteristic equation, and for our system we have B and A as given here, and here is Phi CL. We substitute in this Aryabhata's identity and arrive at SC and RC as given here. This expression is the correct one. In the book, the second factor here is missing, but everything else in the book is correct. The simulation results are correct, only this second part is missing. You may want to make a note of this. Notice that both the factors of RC are bad. Here it is negative, here it is outside the unit circle. We will use the same Scilab file dof_choice.sce. The only difference is now you have to set control equals 1 in this file. Where do you do this? It's in the next slide. I show it as 2, but you have to take it as 1 and design the controller. Now for both controls, you have to execute this file dof_choice_param.sce. What it does is it invokes this xcos file and sets the limits for plots, and it invokes the simulation. Here is the screenshot of the xcos diagram. Now I will compare the controller performance. Thick lines are produced by the cancelled controller. You can see that thick lines are here, whereas the thin lines are produced with the uncancelled controller. You can see that uncancelled controller has large oscillations. So cancelled controller performs a lot better. It produces much less oscillation and also much less overshoot. Look at the overshoot here. It's very small here. Here it is lot larger. I have a homework for you. Repeat all the examples that we discussed in this week without cancelling good factors. We cancelled good factors in all examples. I would want you to redo all of them without cancelling good factors. I myself carried out for the magnetically suspended ball problem, and cancellation produces much better result. But I would want you to verify that for all examples. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.